So in 7.3, we now look at the special case of rotational equilibrium just in the same way as in Unit 2, we looked at the special cases of Newton's laws that involved translational equilibrium. So now we'll look at the specific case of rotational equilibrium in order to add an additional condition for overall equilibrium to occur to an object that may be both rotating and moving from one spot to another. So consider the following scenario. A person pushes on a door in the negative y direction, while another person pushes in the plus y direction with an equal magnitude of force. We ask, will the objects be in equilibrium? So based on what we learned in Unit 2 with Newton's second law, we'd have that our net force in the y direction is equal to 0. So we would be tempted to say that yes, our object is in equilibrium. Well, let's consider the following scenario here, okay? Let's say that our object is free to rotate around this axis right here. So our person who applies the force downward in the negative y direction is going to be pushing on one side of our object, while a person who is applying the force in the upward direction is applying it on the other side of our object. Here, F2 and F1 are different forces because I couldn't find a better visual. So just imagine for a moment that F2 and F1 are equal forces in magnitude, okay? So even though we have a net force in the y direction of 0, we can see that this person who's pushing on this side of our axis of rotation and this person who's pushing on the other side axis of rotation is going to cause our door to accelerate in the counterclockwise direction. So as a result, our object is not in an overall state of equilibrium because even though the net force is 0, the net torque is not going to be 0. So the net torque again is not 0 since the torque acting on the door is in the counterclockwise direction. All our forces are causing a counterclockwise acceleration, angular acceleration. Thus we see that we have a new and final condition for equilibrium to occur. So the first condition that we have is that the net forces must be balanced in all directions. Net force in the x direction, net force in the y direction, net force in the z direction must all equal 0. The z direction we don't have to worry about in this class, but we can consider a z direction if we wanted to. Okay, and then the second condition is that the net torque on the system must be balanced. Okay, so we can also see scenarios that are also the opposite of what we have going on here, where we can have a net torque of 0, but a net force that is non-zero. And we'll explore such scenarios in class. So the problem-solving process again is the same as we saw with Newton's second law back in 7.2, and also like we saw with equilibrium, translational equilibrium back in Unit 2, except now we have the additional step of identifying what the problem is asking us to solve for. So we draw a free body diagram representing the forces acting on our object, just as we always do, and then we identify what the problem is asking us to solve for, acceleration, a particular force, etc. Because sometimes there may not be an equilibrium scenario and we may have to solve for acceleration. Other times, it may be an equilibrium scenario where we have to solve for a particular force. And that's where we come to our third step. We have to determine if the system is in equilibrium. So again, we have to determine, is our system at rest? Is there a constant speed, constant angular velocity, so on and so forth. And then lastly, we sum together our torques, or better than said, not lastly, but I guess the penultimate step. We sum together our torques, not forces in this case, and we solve for the unknown quantity. If we are looking for forces, say we're looking at a translational equilibrium scenario, we'll sum together our forces. But here we're looking at the particular example where we're looking at a system that's in equilibrium, a rotational system is equilibrium, and so our main object of interest is going to be the torques acting on a system. And then lastly, we solve for our unknown quantity using Newton's second law in equilibrium. So in addition, with static equilibrium problems, the nice thing is that we are free to choose the axis of rotation. Meaning we can choose where our system is going to be rotating at or would be rotating if it was in equilibrium. And this is a very useful technique because it can be used to eliminate unsightly or ugly parts of a problem, like let's say a torque that we don't know the value of. We can use that to eliminate the torque that we don't know the value of and make the problem simpler on ourselves to solve, as we'll see in the next example. So a rigid bar, in this example here, a rigid bar with a weight of 100 newtons is free to rotate about a frictionless hinge at a wall and supported in a horizontal position by a spring scale attached to the ceiling at an angle of 30 degrees to the vertical, as shown. We ask, what is the force of tension that's indicated by a spring scale? Okay, if we have the spring scale right here, what is the tension, what is the force that's going to be right on the spring scale? So first thing we need to do is we need to draw a free body diagram, okay? So we're going to have the tension right here, all right, acting at an angle of 60 degrees with the bar just by making use of a right triangle. So if this is 30 degrees, the angle right here must be 60 degrees. We have the force due to gravity that acts at the center of mass of our bar. And then lastly, we actually have a force due to the hinge that acts at an angle right here, okay, which we haven't seen before. But the reason why we have a force due to the hinge right here is because if this hinge right here was not applying a force, okay, our bar would swing downwards like this right here. Our bar would swing downwards. So the hinge applies a force in order to keep our bar from swinging downwards, okay? If you're asking why does it act at an angle instead of straight up, okay, the hinge right here is going to be pushing upwards in order to prevent our bar from falling, and then it's also going to be applying a force to the right in order to counteract the force of the spring scale that's also going to be acting to the, let's see here, actually, do I have that right? I may have my force of the hinge acting in a slightly, no, it's in the right direction here. So you can see right here, this hinge force does trip people up a bit, but as you're going to see, because we can choose our axis of rotation, this hinge force is not going to be a problem. So even though it's causing a problem for me right now, what we're going to see is I can choose my axis of rotation to get rid of this problematic hinge force that's causing me such a headache right here. All right, this is what our free body diagram looks like. Again, we have the tension acting at a 60-degree angle. We have the force due to gravity of the bar acting as center. And then we have the hinge force that's pushing upward and to the right to keep our bar from falling to the right, to keep us from falling down and rotating downwards. All right. So we now ask what we're trying to solve for. We're trying to solve for tension T. And now we ask if we're in equilibrium. Yes, we're in equilibrium because this is a static equilibrium problem. Our bar is not moving at all. So as a result, our net torque is going to be equal to 0. So now what we're going to do is write down the torques associated with each of the forces. So we're going to have the torque due to the hinge, which in this case, we're not going to worry about whether it's a plus or minus because we're going to see that the torque to the hinge drops out. It's going to actually be 0, so it can't be plus or minus. The force due to gravity is pulling downward our bar, which is going to try to cause a clockwise rotation. So we have negative torque due to gravity, and we have the torque due to tension that is acting upwards and is pulling up, which if the tension would cause a counterclockwise rotation. So we're going to have a positive torque for tension right here. And all of this is going to be equal to 0. So now what we're going to do is now we add in the equations for torques for each individual force. So what we're going to do here is we're going to choose this spot where the hinge acts to be our axis of rotation, with the idea being right here is that if we cut our tension rope right here, our bar would rotate downwards in the clockwise direction about this hinge right here, okay? So we're going to choose our hinge to be our axis of rotation. We could also take the tension to be our axis of rotation because if the hinge wasn't here, our bar would swing downwards in the counterclockwise direction. But in this case, the reason why we're going to choose the hinge to be our axis of rotation is because, as I noted before, we don't know anything about the hinge force. We don't know what the hinge force is. We don't know a numeric value for it. So that's going to be a problem that we can't solve for. And that's going to complicate things, make life difficult for us. So if we take our axis of rotation to be where the hinge is, that means the force of our hinge acts at a distance of 0 from the axis of rotation, which means our torque is going to be the force of the hinge times 0, the distance from the axis of rotation. So this hinge force is going to drop out, and there's not going to be a torque caused by this hinge force, which is quite nice. Now we move on to force due to gravity right here. So if this bar has a length of L right here, which we'll just call L for time being, as we'll see, the length drops out, and we actually don't need the length. If this bar is a length L, then the force due to gravity acts at a length L over 2 at the center of our bar. And this force due to gravity also acts at an angle of 90 degrees with our bar. So as a result, we have the sine of 90 degrees. And then lastly, right here, we have the tension right here that acts at a distance L from our axis of rotation. Again, if this whole bar is a length of L and this is our axis of rotation, tension acts at length L. And then this angle that tension makes with our bar is 60 degrees, so we're going to have the sine of 60 degrees. So what we can notice right here is that since this is 0, each term contains L. And since this whole equation is equal to 0, we can divide both sides by L in order to get rid of L. So as a result, we're now going to have minus Fg divided by 2 plus tension times rad 3 over 2 equals 0, where rad 3 over 2 comes from the fact that the sine of 60 degrees is equal to the rad 3 over 2. So now we can get rid of 2 in this equation by multiplying both sides by 2, which gives us minus Fg plus tension times rad 3 equals 0, or tension equals the force due to gravity divided by rad 3, which we get after solving this equation for tension. So that's going to give us tension equals 1,000 newtons divided by rad 3, which we can leave as that, and if you want the full answer, you can put it into a calculator. So here's an example of an equilibrium problem with rotation. Again, the big hint here is that we can choose our axis of rotation to be what we want. Either it could have been where the tension was, or it could have been where the hinge was, but since we don't know what the hinge value of the force is, we choose the axis of rotation to be here to get rid of that force of the hinge. And then we apply the usual steps that we've done, going back to Unit 2. Now this may be a lot easier said than done, as things typically tend to be with physics, but for right now we're just familiarizing ourselves with the process, and then in class we'll get exposed to a lot more practice problems.